Well, thanks, Paul, and I appreciate the chance to be here and talk to you all. I thought it would be fun to start out, since I'm a professor, I feel the need actually to start out with a pop quiz. And so we'll see how this goes. So I have two stars here, and first I'm going to ask, what's the one on the left? Does anyone besides Phil have a guess? It's okay to guess, you don't have to actually know. Good try, Joe. It's actually not the sun. Alpha Centauri, good job, Ricky. Yeah, that is Alpha Centauri A, actually. And the spectrum that's sitting beneath it is a spectrum gathered by the Hubble Space Telescope. So it's just a piece of that spectrum centered around the carbon-4 lines, around 1550 angstroms. And here I have another star, also with its FUV spectrum. Does anyone want to guess what that one is? That one is the sun. Did you just guess that because you read the abstract, or have you seen this picture before?
I studied for the exam.
Good job, Alfred. So the picture on the right was actually taken by Voyager, and the spectrum was not taken by Voyager. The spectrum is from source. Even at this sort of poor resolution that I've put the spectra up here, you can see a significant difference between this Hubble spectrum and the source spectrum. It's just a matter of resolution. The carbon-4 lines they look a lot closer together here because they're wider. And the carbon-1 lines here are actually blended together. And so, I mean, obviously the wonderful thing about source is that it's up there all the time. It's giving us well-calibrated spectra on a very frequent basis, which we don't get for any other star. But on the other hand, if you care about line profiles, you really can't get a whole lot. So that's the prelude, and it's intended to help motivate a rocket mission that I call FURST. Turns out there's a German word FURST, which actually means first. So it's my first rocket, but it's my third rocket, or maybe my fifth rocket, depending on if you count graduate school and all that. So it's all a little bit confusing. So what I've been trying to say here is that the solar ultraviolet spectrum, particularly between about 1,000 and 2,000 angstroms, is actually sort of poorly known, at least on a sort of full sun, full disk kind of basis. And the Hubble Space Telescope, by contrast, has given us wonderful high-resolution spectra of a bunch of other stars. So what could we learn if we actually had a full sun UV spectrum over that range? There are several answers. One concerns the sun as a star. So the sun and other stars have chromospheres that are heated somehow or other. And we don't really understand that very well. It may be that by putting the sun in the context of other stars that have chromospheric heating and transition region and coronal heating to different degrees, we might actually learn something by comparing the spectra. So for example, you might be interested in what the importance of small-scale magnetic reconnection is in explosive events. These are things that cause line broadenings and like carbon-4 and silicon-4 and things like that, right? It would be interesting to see how those kinds of events contribute to the full sun spectrum. Likewise, moving away from stellar physics, we could talk about general solar system physics. If you have a comet, let's say, that's approaching the sun pretty fast, as comets are known to do, it sees a blue-shifted version of that spectrum, right? And so if you want to know something about resonant excitation in that cometary atmosphere, you'd better know the line profiles for Lyman alpha and some other lines if you're going to understand what's going on. And in fact, even if you don't have a Doppler shift problem, even if you're just looking at Jupiter or something, the width of that line on the sun matters, because if it's really broad, then there's less of it in that narrow absorption core in the planetary atmosphere. So there's a lot that we can learn from this. what I'd really like to do is just propose a satellite mission and get this over with, and do something like SOURCE, only at really high resolution, and then we would have a spectrum every day, or maybe several of them, and then we could kind of put the problem to bed. But we decided first to propose a sounding rocket flight. It's a good way with a new kind of instrument and something that hasn't been done before to get it off the ground quickly and learn everything about your instrument. But before we go that far, we might want to know whether we could actually piece together what we need to know from existing data. These are, on this table, examples of missions that have collected full sun spectra in the relevant wavelength range. And you'll see that none of them do better than an angstrom for spectral resolution. So if, as I claim, line profiles are important for the science, then you can't get there with these. Well, that's not the only choice. You might also wonder about instruments that have very high spatial or high spectral resolution, like SUMER, for instance, or IRIS, on which I'm a co-I. And so we can start to appreciate why this becomes a hard problem by looking at some SUMER data here. Here's a center-to-limb profile of some SUMER UV continuum, and then here's the carbon-4 1548 line. And as many of you already know, you get a lot of limb brightening out of an optically thin line, right? So the center-to-limb profile is not trivial. So what you cannot do is just point your telescope at somewhere in the middle of the sun, or at the limb of the sun, or at an arbitrary place, and collect a full spectrum that can be compared directly with full disk spectra of other stars. The center-to-limb behavior is different in every spectral line and in the continuum. It also differs as you look at active regions and coronal holes, quiet sun, and other phenomena like sunspots, right? So piecing one together, piecing a full disk spectrum together, really requires scanning the full disk. Now, it's not like that hasn't been done. SUMER has done some full disk scans, but only in very narrow wavelength ranges. Likewise with IRIS. With IRIS, we use a very short line list when we're doing our full disk mosaics once a month. And so if it's any help, you might look at the diagram that I mysteriously put on the board earlier. On the horizontal axis, I have wavelength from 1,000 to 2,000 angstroms. And then on the vertical axis, I have solar radius from 0 to the radius of the sun. Now, I don't really mean for that vertical axis to only denote radius, because, as I said, there's also this matter of different kinds of phenomena on the disk, right? Like active regions and quiet sun. But the horizontal bands that I've drawn there represent the idea of essentially trying to piece together a full disk spectrum from using a few pointings, not very many on the sun. So that's the sort of thing that you would do if you had the Hertz Atlas, right? Some of you have probably used the Hertz Atlas. It's a wonderful set of sounding rocket observations that cover our entire wavelength range. And so that's why I drew those as, horizontal skinny rectangles, because they only had a few pointings on the sun, right? And then the vertical skinny rectangles, those are what you get if you take an IRIS full disk spectrum, or a SUMER full disk scan, or at least something close to a full disk scan with SUMER, right? So we can try to cover this big square that's on the board in little slices and hope to piece it together. But in reality, we're likely to miss a lot of things because there are lots of different kinds of behaviors in the spectral lines that we look at as we move from object to object on the surface of the sun. So my argument is that we really cannot piece this together. Here's a nice little example. So on the left is some solar spectrum, a little chunk of it from SUMER. And on the right is Hubble STIS data from Alpha Cen A. And there are a number of things that you notice that are different about these. It looks like the continuum's at sort of the same level, but the spectral lines apparently are a lot taller for Alpha Cen A. That's actually likely just an effect of the observation, because I think this data was taken at disk center, if I remember correctly. And so we don't have that that effect of the greater path length that you get as you approach the limb of the sun that would add so much more to the line intensities for optically thin lines like oxygen-4 and silicon-4, right? So that explains part of the discrepancy. It's also, this also is an interesting diagram because you see a hint of broad wings in these emission lines in the STS spectra from alpha Cen A. It would be really interesting, wouldn't it, to know whether alpha Cen A has more transition region explosive events than the sun does or less, right? Does it have a more active transition region, a more active atmosphere, or a less active one? At least by this measure, that would be one way of finding that out. Now this is an eye chart, and I apologize. I don't mean for you to read it. I mean for it to remind me what to say. But as we came up with this project, we came up with a number of requirements. One is that we wanted accurate radiometry, plus or minus around 5%, so that it would be worth comparing with the Hubble data to put the sun in its context with other stars. We wanted spectral resolution of 10,000 or greater. Here I've written 20,000, mainly because we managed to do that with the design, not because we really would have to have 20,000. Even 10,000 would give us a lot of information on line profiles. We would like to cover the 100 to 200 nanometer range, and there's a range of, kind of a small selection of interesting lines here. We could have written down a lot more, but things that we would like to specifically compare. We would like our wavelength calibration to be good to a few kilometers per second. And we would also like to have good enough signal to noise that if we look, say, in the 150 nanometer continuum, we really measure the continuum. So maybe a signal to noise of 10 or 20 or so to 1. On the other hand, there's a really bright line at 1216 angstroms, Lyman alpha, right? And if we have a really sensitive spectrograph, you might wonder whether we're going to saturate that thing. So we would like to, by some means or other, get a really wide dynamic range so that we don't saturate in the Lyman alpha, even if we're lucky or unlucky enough for a flare to occur when we launch this thing to point at the sun. By the way, feel free to interrupt me. I don't mind being interrupted by questions. I'll leave some time at the end for questions too, but I'm more than willing to be sidetracked, derailed, what have you. So personally, as a person who has always tried to get higher and higher spatial resolution, I had a difficult time mentally coming to grips with the idea of looking at the entire sun and not having, not spreading it across 1 million pixels or, 16 million pixels as the case may be, right? That's about what you get with AIA. So I had to really, kind of bend my mind around to think about this. And the first thing that occurred to us, and I have to give Phil credit, by the way, he's the one who really raised all of these issues to my consciousness. If you had asked me, do we have a good UV spectrum for the sun, I would have said, what, are you kidding me? This is the 21st century. Of course we have a good UV spectrum of the sun, right? Well, so the first idea that occurred to us was that if you put a little ball bearing out in front of Hubble, then it would reflect the sun, of course, reflect the sunlight. It would form a virtual image of the sun inside the sphere, right, halfway between the center and the surface of the sphere. You'd form a virtual image of the sun. It would look like a star, and so you could just take a spectrum of the thing with the Hubble, right? That'd be just fine. But we talked about that for a while, and we couldn't really convince ourselves that we would be able to convince anyone else to do this. And so we thought about how to actually just design an instrument from scratch. So the starting point was, well, let's feed our optics with a ball bearing. But then it occurred to me that, if I'm making a round thing, it doesn't have to be a sphere, it could be a cylinder, and that would actually have some great advantages. It works a lot like a spectrographic slit. If I form, and this is greatly exaggerated in size, but if I have light coming in from the sun from the left here, it forms this virtual image that, like I said, is halfway between the center and the edge of my circle here. And because the circle is really a cylinder, not a sphere, it's a sort of a tall, skinny, spaghettified sun, okay? So when I image that through a grating onto a detector, right, a spectral line turns into, well, a line, which is what you want. It works just like a slit. but it gets you the whole sun. It's important, though, that this virtual slit, or this virtual solar image, be quite narrow. And so we have sized our cylinder so that it makes a 15 micron image of the sun. That requires a 6 millimeter diameter rod here. And so that light spreads out from the little rod, and it feeds a grating that happens to be like 8 inches wide, the biggest grating that we could fit in without unacceptable aberrations. And that, in fact, really helps to capture the largest amount of light possible, since the solar radiation is spreading out in all directions from this little cylinder. And then it comes to a focus on the detector. The elements of a little image here, a little image here, and both of those being on this thing called the Rowland circle, that's an idea that goes back to the 1800s, oddly enough, to a guy named Rowland. And so this is how a lot of spectrometers are built. That's also why you want sort of 15 micron or smaller sun if you have 15 micron pixels. So that's the general design of it. And then the next question is, well, how do we get all the wavelengths that we want? Because our detector is only a couple thousand pixels wide. That's not enough pixels to get all the resolution elements that we want between 1,000 and 2,000 angstroms. And so the easiest, or maybe most obvious answer, easiest is the wrong word, is to put this cylinder on some kind of an arm and swing it around, right? So you could scan and get different wavelength ranges by swinging around the Rowland circle, because you change the angle of incidence to the grating. That changes the wavelength that you get off. However, that would require a pretty complicated mechanism, and it would have to be very precise to get the kind of wavelength calibration that we want. So we thought, well, why not just have a bunch of cylinders? Here they are. It's a bunch of cylinders that the light can shine on. We'll only let the light shine on one of them at a time, though, and then whichever one is open to the sunlight will illuminate the grating and form images on our detector over here. So this is actually an engineering drawing, kind of a preliminary one of our design. It ends up that we need 9 of these rods over here. And of course, we need a way to only look at one of them at a time. So how do we do that? Well, we came up with the idea of these little photo booths, or whatever you want to call them, that they can sit in. Okay, it's like a little cylindrical piece of sheet metal that's probably black anodized or something like that, and it's got a slot on it that allows the sunlight through. And if you don't want the sunlight to hit that particular rod, then you just spin it, right? Spin it away from the sun. So we have this series of mechanisms. I, being a rocket guy, hate having 9 mechanisms on my payload because it makes me think one of them is going to fail. But the thing about this is that these are exceedingly simple. There are no gear drives or worm gears or anything crazy like that. We just have direct drive from, let's say, it could be a stepper motor or some other kind of a servo motor, directly to this little thing that isn't resting on anything other than the motor bearings. It doesn't weigh anything. So it can be moved very fast, and it can be made extremely reliable. So I really have no worries about this. We should be able to spin these little things and change channels as quickly as we want. The other beauty about this is the detectors, which are frame transfer CCDs that actually were designed for our ESIS sounding rocket mission by the good folks at Marshall Space Flight Center. A couple of them will be coming out to join us. Amy Weinbarger and Laurel Rockmeller will come out the Thursday and Friday of next week, and I'll have a couple of guys down from MSU also to work with us, and we'll have a little kickoff meeting to kind of get going on this project. But the beautiful thing is that since we orient our frame transfer CCD so that we slide the image off of it and under a mask in a direction perpendicular to the dispersion of the grating, okay, so perpendicular to the wavelength axis. If there's any smearing at all, we smear along the spectral lines. So in effect, it doesn't change our spectral resolution, right? It's essentially perfect. So what that means is between these and these really fast little shutter motors, we can observe practically 100% of the time. We only get 5 minutes in a sounding rocket launch anyway, right? 5 minutes above about 150 kilometers, let's say, to take this data. And so we want to take the best advantage of that time that we possibly can. So that's how we went about that. And it turns out that this design that we have for our other sounding rocket, we can essentially use the same design with no modifications whatsoever. We just bolt it onto the new optical bench and it'll work. So that's that. We went to a certain amount of trouble ray tracing this because we have a lot of scenarios, right? We have all these feed optics at different points along the Rowland circle, and we have a really big diffraction grating that's probably going to have some aberration because it's so wide. And then we have our detector, and we have within the field of view of each one of those feed optics a wide range of wavelengths, right? So we wanted to essentially check all possible cases, and my grad student Roy Smart stepped up to that challenge, and I had written kind of a dumb little MATLAB program to lay out the spectrograph because I'm lazy and I don't like doing things by hand. And then he took that and actually interfaced it with Zmax so that we could in effect run all possible cases, all wavelengths and all channels. And so we got out of it histograms like this, which are essentially point spread functions, or I suppose I should call them line spread functions. And if you look at the little bins here, these bins are actually 1/4 of 1 pixel. So what it means is that in the narrowest case here, we barely managed to resolve our point spread function. It's important to resolve the point spread function. We don't want it to be narrower than a pixel because then it would make it really hard to measure Doppler shifts and things like that, right? And it would also make it really hard to interpolate the wavelength axis. So it's important to have more pixels than you need for the resolution that you want. So then here are a couple of other cases, and in the end we combine thousands of these to produce a plot like this, which each of these lines, so the red one represents looking at the center of the detector over a range of wavelengths. This is as if we were taking one of those feed optics and just swinging it out across, the Rowland circle, but always looking at the center of our detector. And from this plot, you can tell that we didn't optimize the design yet because we've got best focus in the center of the detector and not as well, no, that's wrong. I've got it the other way around. This is resolving power, which is lambda on delta lambda. So actually we have the worst focus at the center of the detector and the best at the edges. But we could probably reach a much better compromise by tweaking that up a little bit. The thing is, we didn't have to. We didn't have to for the proposal because all of these curves are well above the 20,000 that we set down in our requirements table. And so we really have tremendous spectral resolution, up in many cases over 30,000. So it's a tremendous spectrometer, really, as it turns out. This is kind of the summary of the performance that we got. Signal to noise, I wanted 20 in the 150 nanometer continuum. We ended up with, our best guess right now is 200. So order of magnitude better SNR than the goal that we set for ourselves. Remarkably, it is not possible to saturate in Lyman alpha. And the main reason for that is that we're not collecting one spectrum, we're collecting 1,000 of them, right? Because our detector actually has some height. It was meant to be an imaging detector. We're kind of, abusing it in a way, I feel, by not making images. but because we essentially have 1,000 pieces that every spectrum is constructed from, even if we have an X-flare going off on the sun, we're not going to saturate in any pixel. So we have tremendous dynamic range with this instrument. Let's see, I guess that's all I wanted to say about that. About 5 picometers per pixel along the wavelength axis, which is really pretty nice. Calibration is our other tall pole in our tent. And so we have scheduled and budgeted for a trip to the SURF 3 synchrotron in Gaithersburg, Maryland. The spectral irradiance of their beam is known to better than 1%, and so hopefully our 5% accuracy goal can be met. The challenge will be making sure that we don't manage to degrade any of our coatings or detector or deposit contaminants in the course of calibrating this thing, which is always hard in the far ultraviolet. Then the next calibration issue is wavelength, because the SURF 3 source, of course, it's synchrotron, it's continuum. There are no spectral features whatsoever unless you stuff a filter in or something like that. So So we have, as it turns out, because of my colleagues at Marshall Space Flight Center, this wonderful calibration section. It's built into a set of rocket skins. You just bolt it onto your rocket payload. It has a place to put various kinds of discharge lamps, and it serves as a nice spectral line source for calibrating a spectrograph. So by using a variety of different line sources, we should be able to cover all of our wavelength ranges, our sub-channels. And it should give us a very nice way to calibrate this thing. Also, if it should happen, God forbid, that we have some awful contamination event and manage to, degrade the sensitivity of our instrument, this will help us to realize it because the clasp calibration section is portable. Now, it doesn't have the kind of radiometric stability that a synchrotron does. Nothing has that, right, other than a synchrotron. But at least if there's a big change, we'll know about it right away because we can take that thing into the field with this calibrate immediately before and immediately after flight. If there's some shift, in alignment or something like that, we'll know about it right away. So that will provide us a tremendous amount of confidence, hopefully, about the data that we've gathered. So, gosh, that went really fast. I thought this was going to take an hour. But the summary is that FIRST will be the first to observe the full sun, and VUV, you see what I did there. And there are lots of applications for it in atmospheric and climate science here on Earth, solar system science, solar and stellar physics. So we hope this will be a truly interdisciplinary mission. That actually gave me a little bit of fear in proposing it, by the way. Has anyone here ever tried to propose a really interdisciplinary thing to either NSF or NASA? Because my experience has normally been that it falls between the stools. They don't know which panel to hand it to, right? I mean, we all agree, and generally the people at the funding agencies, I think, morally agree that interdisciplinary is good, but it's very hard to figure out how to treat it, right? Fortunately, though, we did manage to get it funded, and we're spinning up the program. As I said, we've got some visitors coming next week as well to help us so that we can work through the schedule and the difficult engineering challenges and things like that and get ourselves going in the right direction. We plan to launch it in late 2021, and of course to propose future flights, because that's just one spectrum, right? In 2021, I'm pledging we will have one spectrum, finally. And so obviously we would like to have more after that. And ultimately, what I would really like to do is squeeze this thing somehow into like a 6U CubeSat, which sounds really hard, and it sort of is. We've got presently a 1 meter Roland circle in our design. That's obviously not going to fit in this area. 6U CubeSat is this big, right? 12 inches by 8 by 4. So how will we do that? I think the keys will be a detector with very small pitch, very small pixels, not 12 microns, but maybe 4 or something like that. And also just simply exploit the fact that it's going to be up there for a long time. It doesn't have to have the effective area that FIRST does, because it doesn't have to get the whole spectrum in 5 minutes. It could get it in 5 hours, right? At that point, we don't care. Well, I mean, it might be cool to get one every second, but first things first. Since this has never been done before, if we could even get one a day, it would be fantastic, right? So.
Why not putting it on the
Space station? Yeah, that would be a possibility. You could propose it for that. It introduces some complications in terms of cost and whatnot. Sometimes people worry about contamination in a space station environment. I don't know that that's really the major problem. The pointing is certainly easy enough for this, right? We just have to point at the sun. We don't have to. I'm used to rocket payloads where we're like, oh my God, the pointing drifted by 10 arc seconds. What are you people, In this case, if it drifts by, a quarter degree, it's not going to be the end of the world. So pointing is easy. Yeah, the space station might work out all right. It would be fun to think about that. What other questions? Ricky? Oh yeah, I guess we're allowed to do that.
Could you say some more words about the physics of explosive events and
Yeah.
how that will appear in these spectra?
Right. Well, of course, the short answer is we don't know, because I'm not aware that anyone has quite figured that out. But there's a nice data set laying around for us to do a first try on. And in fact, Josh Loudon, one of my grad students right here in the back row, has started working on this. We have iris full disk mosaics that have been taken every month since the mission started. And although the spectral range is small, it includes things like carbon-2 and silicon-4, and so we can hope to actually see the signature of explosive events in the full disk spectra, because the full disk mosaics include the information in every pixel, right? I mean, the sun is like 1,000 arc seconds in radius, right? So 2,000 in diameter, and we've got 6 pixels per arc second. So 2 times 6 is 12. So it's a 12,000 by 12,000 by however many wavelengths deep data cube, right? For every month, in every wavelength, and so the idea is we can easily spot the explosive events one by one, pixel by pixel, right? It's easy to write a digital filter that will automatically identify out of those 144 million pixels which ones have explosive events in them. So we can produce an average explosive event spectrum, right, and see what it contributes to the whole sun spectrum, or we can just subtract it from the whole sun spectrum and see if it looks any different, right? I think it will look different. I think it'll be subtle. I think it relies on really good signal to noise to see it, but we have that with this instrument, right? So and I think Hubble has it to the degree that we need it for looking at Alpha Centauri and a whole bunch of other stars. So predominantly what I expect to see are line broadenings. That's what an explosive event is, right? I mean, something's blowing up. Go back to first grade physics here, right? Something's blowing up. That always makes good first grade physics. And then, stuff is moving both toward you and away from you naturally, right? It's a self-similar expansion, and so you see a line broadening. And there are lots of different kinds of line broadenings associated with these explosive events. One of the things that's not known, by the way, and which we might discover by the by in the process of analyzing the iris data, is just how many of these explosive events have significant emission in the core of the line profile. Because there's a certain amount of literature out there to suggest that the core is pretty well filled in, that you get a brightening in the core simultaneous to the broadening in the line profile, all right? And so it's kind of it's a line profile shaped kind of like this, or maybe like that, okay? But there's also a whole series of results, among them my recent graduate Tom Rust, who looked at a whole lot of explosive events in helium-2, 304, from our Moses sounding rocket flight that have line profiles like this, okay, like a gull wing, with a void in the middle. And if we go to the trouble of deconvolving our line spread function from these, we may even see like almost zero emission in the core, right? So those are very different spectral signatures. Apparently there are both kinds of explosive events on the sun. Things that have, a thing slinging toward you and a thing slinging away from you and nothing in the middle, all the way to stuff that, is bright all across the line profile. So what the heck is that? And what proportions do these actually occur in the solar atmosphere? I don't think there's a paper on that anywhere. But probably from as big a survey as all of the iris full disk mosaics, we could actually conclusively answer that question, at least for the silicon-4 line, if not for anything else.
Very, very poor measurement. Okay. That made you ask yourself why it hasn't been done.
Yeah.
But because, yes, you convincingly laid out the comparison to all the stellar measurements are essential. Nevertheless, then, as you also pointed out, one wants to immediately go beyond that and wants to see with detailed measurements how the full disk signal comes about. So here's my question.
Mm-hmm.
In the lines that through iris you have available to do this kind of composition to then figure out what your whole sun signal will be. Mm-hmm. Are there that would be essential for the stellar signal.
Right. Lines that are missing from the iris list, you mean? The iris full disk mosaic list. Well, most of them are missing. And, I mean, the best that I can do is give kind of a positive answer that we have really good data on silicon-4, magnesium-2, and carbon-2. Right? And there are a few other lines in there, I'm sure, because there always are. And we have, with so much data, even weak, some of the weaker neutral lines ought to come out very nicely.
But you don't have Lyman
But
alpha.
no, Iris is not capable of getting Lyman alpha, and yeah, so that's just completely off our map, right? Iris, even if you were taking the full detector,
I would assume
yeah.
that is an important line.
Oh, I think it's very important. It's especially important when you get into the atmospheric and climate science, the solar system science, and so on, right? I mean, if you're going to resonantly excite, I don't know, the atmosphere of Io or something like that, I would think Lyman alpha would be a good place to look first. But yeah, you're right. We don't have that. And about the best that we can do is to piece things together, right? I mean, we have this wonderful Hertz atlas that does have Lyman alpha in it. And we have that spectrum for several features. There is a spectrum somewhere in the quiet sun near the limb. There's quiet sun near disk center. There is an example active region that's, I think, sort of close to the limb, and one that's closer to disk center, if I remember right. It's been a while since I looked at the Hertz atlas, so somebody correct me if I'm saying it wrong. There's a coronal hole spectrum, okay, but only at one particular distance from the solar center. So we've got a little bit of information about how Lyman alpha varies in its line profile on the disk, but only a little. And we will have, Lyman alpha line profiles from the whole disk. So we can do a lot with that, I think, at least a lot more than has been done once we have this to back it up. But you're right. I mean, what I wish for is, a Hertz in orbit that scanned the sun all the time. But, it's going to take us a while to convince NASA to put that up there, right? There are a lot of priorities out there. Yeah, Ricky.
Will this allow us to know the solar UV sun of the star spectrum better than Hubble? Signal to noise higher and resolution higher?
I'm not an expert on STIS or on the other spectrometers on Hubble, and I am not prepared to answer that question. I've looked at the spectra, though, some of them, like this one from Pagano et al., and I'm tempted to say, yeah, actually we'll have much higher signal to noise than that, but I could be wrong. I think Hubble is doing an amazing thing, right? It's got a big mirror, but the stars are awfully far away. It's exactly the opposite problem to what we're trying to solve with the sun. And so we have it easy, but Hubble has it hard. And I'm grateful that they've been willing to stare long enough at stars to get at least this good of a spectrum. Probably you'll do better by doing some fitting, right? Because I think arguably, for things that are not neutral lines, for things like silicon-4, this is really over-resolved, right? They've got a lot more pixels than there are thermal line widths within this profile, right? And so probably the features are very well over-resolved, and some kind of careful, low S smoothing or something like that might do a very good job of cleaning this up.
But the spectral resolution is sort of on the higher side.
Yes. Yeah, that's right. That's right. STIS is like 10 to the 5. And so, yeah, we have a few times 10 to the 4. So yeah. I mean, if even if you do a dumb sort of smoothing that simply degrades it to our resolution, right? It will certainly clean up a fair bit. Probably get a factor of 2 in signal to noise just by a little bit of smoothing. Yeah.
Those 9 cylinders, is that a problem that they're not all going to be exactly the same?
It really isn't a problem. And I mean, you mentioned reflective properties.
Well,
course, it's always possible that coatings vary a little bit, right? Even if it's all done in the same coating run, different parts of the chamber get more deposition than other parts, and so there can be all kinds of variations like that. But it really all comes down to calibration. If we take this thing to the synchrotron and we take a full spectrum at the synchrotron, knowing exactly quantitatively what that synchrotron spectrum is, then all of that will come out in the wash, right, if we do our job right. The other thing that you might wonder about is the variation in surface properties. I mean, things like, will the radii all be the same and so on? And really, it turns out that that doesn't matter very much. I'm not used to working in this regime. I'm used to thinking that if my mirror has a few extra bumps in it, it's the end of the world, frankly, because I like to have my arcsecond or better resolution, right? But this is not that mission. As long as we make a skinny spaghettified sun that's around 15 microns wide, the width of that thing, right, that gets projected on our detectors is not limited by our aberrations as much as it is by, well, it is limited by our aberrations, but it's also limited by the width of the sun, right? And the intrinsic aberrations of the design, because we're using such a big, wide grating, are a much more limiting factor in the resolution, the spectroscopic resolution, than say any little mid-spatial wiggles on the surface of the mirror, the kinds of things that we traditionally worry about in building far ultraviolet telescopes and spectrographs. Yeah, Phil. Mm-hmm. Yeah, so the way we wrote this proposal from the get-go was that our first data product after launch ought to be a really complete, well-calibrated spectrum that's just available to the community. And because I mean, I don't know about you, but I can't cover all the bases from atmospheric science to solar science to stellar physics and solar system bodies and run an instrument program too. There's no way. So I think one of the beauties of this mission is that there are a lot of let's call them PhD thesis projects in here, right? I don't even know what all of them are. I probably only know what 5% of them are, if that. And so it strikes me that the thing to do is to get it out there, make it well documented enough so that people can just trust it and use it. And obviously, we'll try as an experiment team to be as available as we can for questions. Hopefully there won't be hundreds of people emailing us questions, but if there were, it'd actually be kind of fun. So yeah, I think the more the merrier. Absolutely.
More questions?
Traditionally, my builders had an attitude that sort of they felt entitled to have the data for themselves for a long time, and this was the way they hurt themselves.
Mm-hmm.
Because the more the data is used and looked at, the larger will be the total harvest,
Mm-hmm.
provided that proper credit is given to the guys who built the instrument.
Right. And I understand that attitude because I'm just one guy and I have a few grad students working for me. And I wouldn't like any of their theses to get scooped, right? I mean, that's something that you just sort of naturally tend to worry about. But I'm starting to come out of that mindset and realize that, actually there are so many things that can be done with the data that the risk of that is relatively small. And my students, to their credit, have all told me this. Whenever I ask them, hey, should we let other people use this data or should we just hang on to it? They say, get it out there. They're not worried. They're not worried one bit. And so if they're not worried, I don't think I should be worried. I think also we have some pretty good examples. I'm fortunate that the first satellite program that I worked on was TRACE. PI, Alan Title, decided Let's give the data to everybody. Make it available as soon as we have it. And I don't think anyone on the team ever felt like we were disadvantaged as a PI team, right? The PI team has a natural advantage always because we know the instrument. We'll always have the jump start on things, on getting science out there just because we know the instrument, even if we make it as available as we possibly can to the whole world. So that's the lesson that I have been learning, through my career.
Yeah, and to me the most stunning example was the change in the policy on the Japanese side from Yoko to Inoue. I think Yoko for years was a little bit undervalued because they were much more restricted than they were with Inoue.
As I recall, they had kind of a time period, right? There was like an expiry date on the sole proprietorship of the PI team. So, that was in a way forward-looking for its time. But I think we've come to a point where people just realize that we've got so much solar data out there, and there's so many things that can be discovered from the available data that there's really comparatively little risk of stepping on each other's toes, and a collaborative mode rather than a competitive one is often more fruitful anyway. Thank you guys, I appreciate it. You're such a great audience. Asked so many good questions.